Example 2. Let Sn represent the following statement. 3 plus 9 plus 27 plus all the way to plus 3 to the nth power is equal to 1/2 times the quantity 3 to the n plus 1 power minus 3. Prove that Sn is true for every positive integer n. All right, so another example of mathematical induction. I have this example laid out exactly like the previous one. I'm just going to walk you through the proof. The first thing we're going to do in part A is verify S1. Okay, this is the base case. So we need to prove that the statement is true for n equals 1. So I am going to write down if n equals 1, S1 becomes what? All right, so we're going to go up here to our original statement. N has to be 1, so basically replace n with 1. On the left side, what numbers would you be adding up? Well, if you look at the plus dot 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 plus 3 to the first power, you're starting with 3, you're adding all the way up to 3 to the first power, which is 3 itself. So that tells us that the only thing that's being added on the left side is the number 3 itself. Okay, does that equal what's on the right side? Well, again, replace n with 1. So that would be 1/2 times 3 to the 1 plus 1 power minus 3. Now we're going to simplify to make sure we get a true statement. We're going to have 3 on the left. The right side is going to be 1/2 times 3 squared minus 3. Keep simplifying. We're going to get 3 is equal to 1/2 times 9 minus 3. The right side is going to become 1/2 times 6. So we do get that 3 equals 3. So that's a true statement. So I'm just going to write here, thus S1 is true. So we've taken care of the base case. We plugged in n equals 1 and showed that we got a true statement. Now, we're going to move on to parts B and C, where we are preparing for induction. We are simply writing the statements that are needed for the induction step in part D. So in part B, we are going to write the statement SK. In part C, we will write the statement SK plus 1. Looking at part B, okay, the statement SK, that means we're writing down the statement for the counting number n equals k. So SK is going to be what? Well, I'm going to go to my original statement, and this time the counting number is k. So I'm going to replace every instance of n with k. Like I said, just go here, scratch out the n, and replace it with k. Okay, so the left side is going to be 3 plus 9 plus 27 plus all the way to 3 to the k. All right, so we're going to have 3 plus 9 plus 27 plus, we're adding all the way to 3 to the kth power. Okay, on the right side, if we replace n with k, we will have 1/2 times 3 to the k plus 1 minus 3. So I'm just going to write that down, 1/2 times 3 to the k plus 1 minus 3. That's it. Okay, this is the statement SK. This is the statement for when n equals k. Okay, that's all we're doing in part B. All right, in part C, now we're going to write the statement for when n equals k plus 1. We call that statement S of k plus 1. Okay, we go back up to our statement. This time your counting number is k plus 1. So you need to replace every instance of n with k plus 1. Okay, so here I'm going to replace n with k plus 1. The left side is going to be 3 plus 9 plus 27 plus, we're adding all the way until 3 to the k plus 1. Okay, I did this in example 1. You should do it every time you're doing induction. It is in your best interest when you're writing the k plus 1 statement that you need to put the k term in it. Okay, so what is the term that comes before 3 to the k plus 1? Well, it's 3 to the k. Okay, why? Look at the pattern here. This is really 3 to the first plus 3 to the second plus 3 cubed plus, if you're ending with 3 to the k plus 1, then the term that comes before it is 3 to the k. Okay, you really need to have that term in here. Okay, it helps you in your induction step when you're pulling from the assumption. Okay, all right, what is going to be on, well, actually, I'll just leave that there. Okay, so what is going to be on the right side? Okay, well, if we go back up to our generic statement up here, again, we are just going to replace in with k plus 1. Okay, on the right side, you don't have to specifically show anything k, just replace in with k plus 1. Okay, so this is going to be 1/2 times 3 to the k plus 1. Okay, that's the n part. N has been replaced with k plus 1, but we have another plus 1 in the exponent. Okay, so make sure you tack on the additional plus 1, and then once you get out of the exponent, you have to subtract 3. Okay, so the red stuff that I wrote down, I was trying to show you the pattern on the left side. So I'm going to go ahead and write the final sk plus 1 statement in black. Okay, it is going to be 3 plus 9 plus 27 plus ... plus 3 to the k plus 3 to the k plus 1. That's got to equal 1/2 times, I'm going to simplify on the right. In parentheses, we'll have 3 to the k plus 2 minus 3. Okay, so going into the induction step, this is our s of k plus 1 that we are trying to prove. Okay, so let's switch over to page 6. Okay, top of page 6, we have part D. Again, the instructions will always read this way in your book and on MyLab Math. Assume that s of k is true and use algebra to change s of k to s of k plus 1. That might be a little confusing, especially with the change part. So basically, the induction step here, all we're going to be doing is we will make the assumption that sk is true, and then we will prove that s of k plus 1 is true from that information. Okay, so let me remind you here that this is the induction step. And the first part of the induction step is assuming that the statement is assuming that the statement is true for n equals k. Okay, so basically we have to assume that s of k is true. So I'm going to write down assume that. I'm going to go back to page 5, back to part B, and I'm writing down sk. Okay, I'm assuming that this is true. Okay, so just go ahead and write the whole thing down. So we're assuming that 3 plus 9 plus 27 plus all the way to 3 to the k is equal to 1/2 times 3 to the k plus 1 minus 3. Write the whole statement down. Okay, we're assuming that this statement is true. We accept it. Okay, now we need to prove that the statement is true for s of k plus 1. Okay, so we need to go back and prove, our goal here is proving that this thing in the box is true. We're proving this, making this assumption. Okay, so we're assuming this, and we're using it to prove this. Okay, to start the proof, we're going to write down the left side of the equation in part C. Okay, so we're going to write then, okay, start writing the left side. Okay, so 3 plus 9 plus 27 plus, you need this term 3 to the k plus 3 to the k plus 1. Okay, that is the left side here. Okay, we have to now work for the right side. We have to use algebra and our assumption. You can't just write down the right side of this equation in black. You start with the left side, you use the assumption, you use algebra to get the right side. Once the right side is achieved, then you're done. All right, so going back to part D here, we have written down the left side of the equation in part C, what we're trying to prove. Okay, now again, like I've said 100 times, we will use the assumption coupled with algebra to obtain the right side. Okay, so what is this equal to? Now is where we use the assumption. The reason it's mandatory to have the kth term here is because it's matching up with your assumption. Okay, this is equal to the left side of your assumption. Okay, so what you see in yellow is the same thing as what's written above. 3 plus 9 plus 27 plus all the way to 3 to the k. That is the same thing as 1/2 times 3 to the k plus 1 minus 3. Okay, so this yellow stuff is equivalent. Okay, on the left side, we still have to add 3 raised to the k plus 1 power. Okay, so that is what this left side is equal to. Now we've used our assumption, and so we have to use algebra to make this new right side look like the right side in part C. Okay, so our goal is now to work what's on the right, use algebra until it turns into this quantity, 1/2 times 3 to the k plus 2 minus 3. All right, so let's see how we can make this happen. There's probably lots of different ways you can manipulate this thing using algebra. I'm going to go this way, okay? But like I said, you may do something else that works out just fine. I'm going to start by distributing, okay? I'm going to send the 1/2 through both terms in parentheses. That's going to tell me that 1/2 times 3 to the k plus 1 minus 3/2. That's what that's going to give me, okay? I still have this plus 3 raised to the k plus 1 power over here, okay? And then I have like terms. This term has a 3 raised to the k plus 1 power, as does this one. So I'm going to combine like terms, okay? I have, if you think about the number in front, okay, so let me basically write it this way so you can see. It's a little weird because we're dealing with exponentials here. This is going to be 1/2 times 3 to the k plus 1. This piece is going to be plus 1 times 3 to the k plus 1. Then I've got just a number hanging around, so I'm going to move it to the very end here. And then what you can do to see this more clearly, here's the 3 raised to the k plus 1 power. Okay, that's common to both of these terms, so you can factor it out. That's going to leave you with 1/2 plus 1. And so that essentially tells you that you have 3/2. 1/2 plus 1 is 3/2. 3/2 times 3 to the k plus 1. Okay, that's how those like terms combine. Okay, you may have been able to see it from as early as this step. Okay, if you have 1/2 many terms and then you're adding another whole one, that's going to be 3/2 terms. Okay, so long story short, when you combine the like terms, you get 3/2 times 3 raised to the k plus 1 power. Don't forget about the constant minus 3/2 that's hanging around. Okay, again, the end goal is to come up with the right side of this equation. Okay, if we keep going here, just keep doing things, okay, and then you will eventually see it. Okay, both terms, the pieces separated by subtraction here, have a 3/2. Okay, so your instinct is to probably factor out a 3/2, but again, remember the goal. There is a 1/2 out front, not a 3/2. So I am only going to factor out a 1/2. Okay, the reason being I'm trying to make it match the goal. If I factor out a 1/2, that's going to leave me with 3 times 3 to the k plus 1. Okay, check yourself by distributing back out. The 3 to the k plus 1 is right here. 3 times 1/2 is 3/2. Okay, and then I'll have my minus sign. If I factor out a 1/2 from 3/2, that's going to leave me with 3. Okay, again, you can distribute by checking yourself. Okay, so what happens now? Okay, again, keep going back to the goal. Okay, the power on the 3 has to be k plus 2. Well, what do I have here? This is really 3 to the first power. And you have like bases. I have a power of 3 times a power of 3, so I'm going to add the exponents. Okay, so the 1/2 will stay out front, and then I'm going to combine the powers of 3 into 1. Power of 3 times the power of 3. Add the exponents. This is going to be k plus 1 plus 1. Okay, this minus 3 is just hanging out. Okay, so it comes along for the ride, and then you can add your exponents. Okay, you'll get 1/2 times 3 to the k plus 2 minus 3. And that is exactly the right side of the equation in part C. Okay, so we are done. We started with the left side of the equation in part C. We used our assumption, we did some algebra, and we ended up with the right side of the equation in part C. Okay, so we can just jot something down that we have done this. Okay, so this final result is the statement for n equals k plus 1. It has been shown that if sk is true, then the statement for k plus 1 is also true. Okay, induction step done. Moving on to part E, we need to write a conclusion about the whole thing. Okay, so we've done the base case. We did that in part A. We did the induction step in part D. So we can write the 2 steps required for proof by mathematical induction have been completed. So the statement Sn is true for every counting number. The proof is done.